So next coming to stage is Alexandru Tsete. So he's working as an embedded software and systems engineer in the aerospace and satcom industry, and he has been active in the open source community, doing open source projects for more than 15 years. He's the creator of several popular open source projects such as gPredict, QGRX. He also enjoys taking selfies of himself of screens displaying gPredict in mighty places. And he has been involved in the LibreSpace Foundation activities since 2016. So Alex will be talking about open source, software-defined radio applications for satellite communication. Thank you.
Thank you, and good morning, everyone. Thanks for being here. Nice to meet you again. Before I start, I would like to have an idea of how many of you know what a software-defined radio is. Come on, more. Yeah. Okay. How many of you are using software-defined radios every day? Yeah, okay, it's almost the same. How many of you have been writing software-defined radio applications? Okay, still good. Well, okay, just to be sure that everyone knows what a software-defined radio is, you know, when you build a CubeSat, you have to talk to it, and you use a radio for that, a radio transmitter and a radio receiver. Now, a software-defined radio is a radio system where we want to do as much in software as possible. And as you can imagine, the reason we want to do that is because software is easier to rewrite and reconfigure. And that way we can have a lot of flexibility. We are not stuck with one specific functionality, but we can try different modulations and data transmission standards. This diagram shows, there are many architectures for software-defined radios. This one shows one of the most common ones that we use today. We start with an RF front end, a tuner, which converts the radio frequencies down to intermediate frequency or baseband, what we call. The important thing is that we can digitize it and process it using a computer. And the computer can be a PC or an embedded device, or depending on the application. One of the software-defined radio applications that some of you probably know is called GQRX, which was mentioned by Luis. And it has a lot of history. It was a long experiment, and as you notice, I no longer work on it. Stopped last year because we ran into several constraints and decided it was time to make something new, which I will talk about later. But it was a very good kickstart for getting software-defined radios for end users on Linux and Mac. Because before that, it was very difficult and took a lot of effort to get it working. When we talk about satellite tracking, those of you who have been around long enough probably started with a Windows PC running a Windows satellite tracking application that had direct support for some antennas and a radio transceiver device. This was very good, except that it couldn't really be reconfigured in an easy way. Then as we started using Linux more and more, we decided to have a slightly different architecture. Some people wrote a library called Hamlet, the ham radio control libraries, which provided a programming interface to various radio and antenna hardware, so that the applications, the satellite tracking applications we wrote, only had to talk one protocol. And that could be either directly over serial port or the network. And the network interface turned out to be very useful because when we wrote software-defined radios and wanted to replace the hardware-defined radios, we could simply plug in to the network interface of the satellite tracking application. And this is how GQRX works, and this is also how SatNox, the SatNox network works when it's controlling the SDR devices. So we can actually run several devices in parallel. As we learned over the years, we cannot have one application that fulfills all our needs. So we identified several wishes we had for software-defined radios. And one is, of course, a graphical console application that we can play with and use interactively on the computer. It's what you usually see when you attach your software-defined radio and have a nice spectrum analyzer, like we saw on this one. As you can see, we have both a real-time spectrum on the top and a waterfall on the bottom, and it's good for visualizing what's going on. In particular, when we have many satellites that are launched at the same time, it can be difficult to know which one is which, so being able to see them all at the same time is a great advantage. The other use cases is like, for example, the SatNogs network, which is just operating unattended. Somebody schedules a pass and you want to receive the satellite when it comes by. Using a graphical tool is not always an advantage. In that case, you want maybe a simple command line interface or a command line application that you can just run, launch when you need it, and stop when you don't need it anymore. Furthermore, a nice application that at least personally, I'm very glad for, is running SDRs over the network remotely. So you don't have to, or you can monitor it even when you're traveling. Maybe when you are at a workshop like here, you can log on to your radio or ground station at home and see what's going on. This could also be useful for things like SatNogs, where currently we don't have any way to see what the ground station is doing or how it's performing. If we had a network interface to it, we could continuously monitor the spectrum and see what the receiver is receiving. So when we decided to try to make these applications, we said, okay, we have GQRX, let's split it up and see what we can do with it. But then we realized that maybe it wasn't such a good idea because so this is actually an outdated dependency diagram of various libraries that GQRX uses. And this is what happens when you don't put sufficient effort into designing your software, but just have an idea and start coding and see what's going on or what happens. This thing works very well when it works, but the problem is, as you can see, we have on the top, we have a GQRX, the application itself. It uses GNU Radio as a framework. Then it uses WebSDR for accessing hardware, which then uses maybe SoftwareDefined or directly interfaces to driver libraries. And the problem is that if you want to package it and distribute it to your end users, you have to package all these libraries together. And as soon as you update, for example, one of the drivers, you have to rebuild everything, and then suddenly you end up spending half of your time packaging and distributing software instead of fixing bugs or adding new features. So we decided to, okay, let's just teach it and start from scratch, see how difficult or how easy or simple it can be. And the first thing we wanted to do is a command line tool because actually that's the easiest to make a simple, like those of you who know or have been using SDRs probably know RTL-FM, a simple command line tool that you just launch and it receives and records audio. It can be done very easily. On the top we have the actual user interface, the high-level application, and below it receiver and transmitter application, which is just some functions that do what you need to do. And we need a signal processing library and, of course, the hardware interfacing API. I think the most important thing to get right is the hardware interfacing API, because as the software develops and evolves and more users come around, they want different hardware devices supported. So getting that right and not making it too complicated is actually the most important thing. So what we decided to do is what has actually already been used in various Windows applications is, instead of linking to the driver libraries at compile time, just load them as if they were plugins. So that makes distribution of the software easy, because you distribute your application and it technically supports all available hardware devices. You just require the user to install the driver libraries that he or she wants to use. once we had these functions, we could easily create a graphical console application by just replacing the command line interface with a Qt user interface. All the rest is technically the same. Of course, some small modifications, but it doesn't require too much. And as you can imagine, if we go from here to the next one, to the client and server, we can technically just cut it off and move the user interface to the client and have what previously was the command line receiver now act as a network server, of course with some proper or added network code. There have been a lot of experiments in this area. One of the most difficult things is getting the latency down when you're using TCP/IP. Some of you maybe have already used WebSDRs. The WebSDR, it's called WebSDR actually on the web. And the problem with the WebSDR was that it wasn't not open source. You couldn't even download it, so we just knew it could be done, but it wasn't available. Anyway, so after some years of work, we are actually have made progress, and we have a command line receiver which has been running as in my ground station, CubeSat station number 13, for 2 years, I think. From time to time, I even forgot it existed. It was just working. Right now, it's offline, not because the SDR is not working, but because the computer, the SBC I was using, actually has started to die after 2 years. So I have to replace it. We have a console receiver, which you can see on the picture running on a Raspberry Pi. That is actually being used for our SDR makerspace work today for testing SDR devices with slight modification. And what else? Yeah, it supports already many devices, RTL SDR, ASPI, SDR Play. It's actually driven by the requirements for the SDR makerspace projects. When that project is done, we can add support for more devices. In the meanwhile, one of my friends has started to work on a WebSDR system in parallel, so I just started working with him a few years ago. This is how it looks today. It's actually very nice. Worked very well in the browser, full screen. I removed the URL because I don't have it running in a way that everybody can just use it, but I can demonstrate it. If everybody is interested, I can give you a demo because this will be released also very soon in a few months, I expect. And yeah, that's basically it. I'd like to conclude it, and if you have any questions, thanks.
Yes, thank you for presentation. So your topic was generally about CubeSat operations with the SDRs. My personal opinion at the moment is that maybe there's already enough YouTube videos how to do the reception of the CubeSats with the SDR. But how you see transmission side? Because when you start transmitting with your USRP or HUG RF, you need to have the power amplifiers, you need to have a much more hardware, you need to do the switching, you need to do your equipment sequencing stuff and like that. How do you see this going forward in the future and in your setup?
Yeah, thank you. Yeah, so transmit support is definitely part of our plans. The way I see it is, okay, so the operator or the ground station designers have to take care of the hardware setup with power amplifiers and filters. Hopefully we can in time develop a set of tutorials or cookbook examples for doing that properly, because it is very difficult. You get most of these devices are sold as test equipment, not as ready to go on the air. So that's a good point. From the sequencing point of view, I think what makes most sense is to use full duplex devices where you can receive and transmit at the same time, because I also think that's how most satellites operate already today, and hopefully at least in the future. So I think, yeah. No? No, okay.
Just a short message for the people that haven't asked any questions yet. As you can see, the speakers don't bite. So I encourage the people that haven't participated yet to just ask any question that you might have. You don't have to be super brave, just ask anything, okay?
Hi, thank you. Nice presentation. And I've been working with Lime SDR for some time now, and I'm developing a communication system for satellite. Have you tried working on FPSK module, FPSK chip in the SDRs? Have you tried building your firmware on that rather than having an external microcontroller? Does it even works?
So you mean to use the processor on the SDR? No. Well, some of the SDRs have a processor on it, like I think it's Ethos Research makes the USRP embedded series. There's the Pluto SDR. I think that's definitely a very interesting option, but I think that's just it's a little difficult to integrate. But maybe they can run the server applications, run as a networked.
So my research tells it's very, very difficult. I was just trying to find out if you guys are thinking in doing that.
Oh, definitely thinking about it. It's the problem is time, as usual. Yeah, I think so. It's really interesting that these devices have the processors on board and you can use it, but I don't have much experience with them yet.
Okay, and regarding the front end, so you were showing a diagram in the starting, flowchart, where you have a front end in the starting, right? So for me, an SDR can work on various frequencies. Is it only the front end that will limit the SDR to work on other frequencies, because your front end would be specific to some frequencies now? So front end would actually improve your signal on some limited frequencies, but it will restrict your SDR on other frequencies, right?
Yes, that's correct. It's because the analog to digital conversion can only go up to, well, typically few megahertz. High-end devices maybe hundreds of megahertz, but still if you want to go up to gigahertz frequencies, you need to convert that down. So therefore, most of these SDR devices have RF front-end integrated. In most cases, that will not be sufficient for high-performance on-air use. You usually need more front-end filters and amplifiers, probably.
Okay, maybe I talk after our presentation.
Sure.
Right? Thank you.
We have time for one more question. The usual suspect.
Okay, I really have some questions, but yeah, we should let some other people talk. So I'll just hand the microphone to Fabian.
Yes, so you mentioned that you plan to, or that there is a new hardware API where you add, where each SDR is added a plugin. So this is complementary to SOAP SDR, so it's a completely different tool, or would you also, because this really needs support, or you need to write a library for each new or not for each existing SDR. So is there a plan to connect to the existing drivers?
Yeah. So if you're thinking about that, making a dedicated API is sort of duplicating the effort that already has been done. You are 100% correct. What is different here compared to SOAP SDR is that SOAP SDR has its own plugin system. It works great. The problem is, and what scares me, is knowing that the way when we distribute it to users, the number of Linux distributions users will use will span like maybe 5, in some cases even 10 years. So the different versions of these APIs that have been installed will be different. Therefore, I think it will be more easier to to have our own API and make sure that we have an interface that's stable and fixed. So we interface directly to librtl SDR, for example, or libAirSpy. Those interfaces are stable because they don't change them anymore. They have the hardware, it's being sold, they just want to sell them. They don't update the interface. Now what we will do is to actually take SoapSDR as a plugin and be able to use, so if somebody comes out with a new device and we don't have time to implement it in our API and somebody else makes a SoapSDR plugin, then we can use that until if it works.
Thank you very much, Alex.